Welcome back to our heat transfer class, where we are delving into the use of numerical methods for solving heat conduction problems within solids. This video was made with the support of InnoEnergy. After the calculation of temperatures and heat transfer rates in a steady state, let us focus on the system of equations for the transient regime, its resolution, and the analysis of results. This lesson is divided into several parts. This video is about parts 1 to 4. Let's start by analyzing the system of equations in a transient regime. Recall that the energy balance method consists of meshing the solid, which is divided into domains, and that the representative point of the domain is the node. The hypothesis is that temperature, properties, and internal heat generation are uniform in each domain. In each domain, we make the energy balance per unit time. In transient regime, we have a system of ordinary differential equations. You have learned to calculate the conductances and to solve the system in steady state. Now, it is time for solving the transient regime. Finite differences method. For the resolution of the energy balance in each node in the transient regime, we will use the finite differences method, which consists in approximating the derivative by a difference. In this approximation, there is an error that is proportional to the time interval. The derivative can be approximated in different ways. For instance, by using the backward difference, the forward difference, or the central difference. This will lead to the existence of different methods to solve the transient regime, as we will discuss later. This methodology consists in dividing time in time intervals that last delta t. The temperature is calculated only in predefined instants. Notice that we use the subscript to identify the position of the node, and the superscript to identify the instant at which the temperature of nodes are calculated. Using the initial vector for n equal to 0, we calculate the vector for n equal to 1. In a generalized way, from the vector at time n, which is known, we will calculate the vector at time n plus 1, which is unknown. It can be seen that the lower the delta t, the higher the accuracy, but we consume more computational time and more memory to store vectors and matrices. Thus, a compromise solution has to be reached. As said before, differences can be backward, forward, or centered. This is an explanation of why there are 3 different methods for solving the transient regime: explicit, implicit, and averaged. Averaged methods are more accurate but more difficult to solve. The key question when solving the transient regime is, in fact, not how the derivative is substituted by a difference, but what temperatures should we use to calculate heat inputs and outputs. The energy balance at the previous instant n is used for the explicit method. The energy balance at the same instant for which we are calculating the temperature, that is, instant n plus 1, is used for the implicit method. Or the average of the heat balance at both instants for the averaged method. The explicit method. Applying the explicit method is equivalent to approximating the continuous function by a step function, assuming that in the interval between instant n and instant n plus 1, temperatures remain at the value they had at time n. This is the step function marked in red color. The energy conservation at point I can be calculated making the energy balance with neighboring nodes at instant n. Notice that if conductances, internal heat generation, and heat capacity change over time, in the explicit method their values at instant n are used. We can find the expression of the unknown temperature at instant n plus 1. The name of this method is explicit because the unknown, which is the temperature at time n plus 1, can be explicitly calculated from the known temperature at time n. In this way, it is not necessary to solve the system of equations at every instant. The temperatures of all the nodes can be calculated one by one at instant n+1. This represents an advantage if we want to make a program that solves the transient regime. Grouping the terms that multiply the temperature of node I at time n. The term multiplying the temperature at instant n can be isolated. This term must be positive to guarantee the stability of the solution of the explicit equations. From this equation, we can find the maximum time interval that allows a stable solution when using the explicit method. This dependence is termed a stability criterion, which can be demonstrated mathematically or from a thermodynamic argument. It represents an undesirable feature of the explicit method because it is not unconditionally stable. In a transient problem, the solution for the nodal temperatures should continuously approach final steady-state values with increasing time. However, with the explicit method, the solution for a delta T higher than the one ensuring stability may be characterized by numerically induced oscillations, which are physically impossible. The oscillations may become unstable, causing the solution to diverge from the actual performance of the system we are simulating. To prevent such erroneous results, the prescribed value of T must be maintained below a certain limit. The implicit method. In the implicit method, the energy balance is made using the values of the instant n+1, which is the one we want to calculate. Is then considered to provide a backward difference approximation to the time derivative. This is equivalent to approximating the continuous function by a step function, assuming that in the interval between instant n and instant n+1 the temperatures remain at the value of instant n+1. Note that when the delta T is very small, the solutions obtained with both methods are very close. The implicit method has the disadvantage that the system of equations must be solved at every time step. The advantage is that it is unconditionally stable, that is, it does not have a maximum delta T like the explicit method. This does not prevent that the larger the delta T, the larger the error you make by approximating a derivative by a difference. Watch the second part on the transient regime to learn how to solve the system of equations and make energy balances.